Today, I would like to talk about our recent study on connecting data simulation and neural ODEs. Okay, so part of this work is a contribution of Mr. Noboru Isobe from the University of Tokyo. So this is the overview of my talk today. First, I'd like to introduce the basics of neural ODEs with the emphasis on the similarity with data simulation method. And then I will review our previous works on machine learning-based approach for model bias correction problem. And then finally, I will suggest the possible use of neural ODE methods for this bias correction problem. This is just our ongoing work, and unfortunately, I'm not able to show any convincing results of numerical experiments using neural ODEs. That is not available here, but I would like to just share the idea and discuss about this idea at the end of my talk. So let's start with the introduction to neural ODE. Neural ODE is an approximate map from a vector x to another vector y. The mathematical formulation is shown here. There are two maps, L1 and L2, usually linear. Transforms the are the transformation from the input and output variables to the latent space variable z. And the evolution of z is described in a continuous dynamics like this. So this is the point that is different from the multi-layer residual neural networks that assumes discrete dynamics like this. So the idea of neural ODEs was first introduced by Chen et al. 2018. And in their paper, it was demonstrated that neural ODEs can be used to fit and extrapolate time series like these spirals. So what is unique in neural ODE is the training method. So unlike the neural networks which uses error backpropagation, training in neural ODE is performed by adjoint method. So this is a loss function as a function of rate and variable z. And the control variable is the initial state and the parameter of the model f. So in order to obtain gradients, we need to obtain the gradient with respect to z all over the integration period. So this gradient is defined as a adjoint vector, and this adjoint is obtained by backward integration of the ODE shown here, starting from the final point of the integration. And this partial derivative is Jacobian of the model function. In the same way, the gradient with respect to parameters can be obtained by another integration using the same adjoint. So the training, there are three integrations. One of them are the forward integration of z, and the rest of them are the two backward integrations of these gradients. And these can be implemented very easily using standard ODE solvers, and they are very effective. So I'd like to emphasize the similarity of this adjoint method with data simulation, namely the four-dimensional variational method. Loss function in 4D bar is defined like this. For simplicity, let's assume the observation is one observation is treated, and the control variable is initial state x0 of the model. And B and R are the matrices of background and observation error covariance, respectively. So in order to obtain the gradient of L with respect to the initial state x0, we need the gradient with respect to x at intermediate time steps. And they can be obtained by backward iteration of these relationships using the adjoint operator. So this is equivalent to the continuous adjoint equation we saw in the last slide. So using this relationship, we can get the gradient with respect to the control variable in this form. So, and I would like to mention briefly the some extensions of neural ODEs. Neural ODE is a map from a single vector to another single vector, which corresponds to the transformation of the latent variable from the one particular time to the target time in hidden state. The neural ODE is essentially equivalent to neural networks. So what is equivalent to recurrent neural networks is neural control differential equation, neural CDE. That it is a map from a latent space variable at multiple time steps to that at the target time steps in latent space. So the integration in latent space is now performed along the path X. That is an interpolation of the input data series. So using the theory of control differential equation. So the theory is a bit more difficult, but the implementation is as easy as ordinary neural ODE. So it can be implemented easily. Okay, so let's move on to the next section. So so far we have been working on the model bias correction problem. In the context of atmosphere or ocean study, model means mostly knowledge-based model with the discretized equations of physical processes. So a model consists of many components like dynamics, moist convection, or small-scale topography, etc. And each component has its own limitation in accuracy due to the finite grid size and limitation in understanding of the basic processes. So basically, model equations are always imperfect and have some systematic error. So hybrid modeling approach, which compensates that systematic error, may improve the accuracy of forecast and also the analysis of data simulation. So there have been many hybrid modeling approaches, and one of them is Patak et al. 2018. So their model is hybrid model combining the imperfect knowledge-based model with an imperfect set of equations and a machine learning-based model, which is in this case the reservoir computing. So in hybrid model, the input of reservoir computing is a combination of state variables and the forecast by an imperfect knowledge-based model. So they show that this hybrid modeling approach is much better than a purely machine learning-based model. But But in their discussion, true time series generated by the true forecast model was used as training data. So which is that is not actually realistic. So in real case, observation is always partial and noisy and sparse in time. So in order to treat such noisy and irregularly sampled observation, machine learning based prediction combined with data simulation was introduced by some recent studies. So one recent study by Brajad et al. Has a model consists of two steps, one of which is data simulation step to estimate the analysis time series from the observation and forecast model. And in machine learning step, the forecast model is updated by training using the analysis time series. And these two steps are repeated for a certain number of times. So to improve both analysis and forecast model. So in their hybrid approach, the model was purely data-driven model, but we can replace this model with the hybrid model. Sorry. Hybrid model combining the knowledge-based model and some machine learning model. So in that approach, the machine learning part can be considered as a bias correction term. And that part can be trained with using the difference from the difference between the forecast and the analysis obtained by the data simulation step. So actually that approach is already popular. So the estimation of bias correction term from forecast and analysis has been done by previous studies with various modeling methods. For example, the study by Danforth and Carney 2008 used the reduced order linear function using singular value decomposition for this bias correction term. And recently, the neural network was used for this bias correction using analysis obtained by 4D bar in operational system. So our previous study used the similar approach. We performed the experiment with Lorentz 96 model with additional term, which is nonlinear. And we generated the observation time series with some random noise. And we performed the data simulation experiment with imperfect forecast model, which is in this case the Lorentz 96 model without additional term. So we performed the data simulation cycle without any bias correction first to obtain the set of forecast and analysis to estimate the bias correction function. And then that bias correction function is applied in the next step before the data simulation step. So we can get the improved analysis with modified forecast. We compared the different models for this bias correction functions. We used both neural network and LSTM and compared with the the case with polynomial regression or more simple first order linear regression. And the result is shown on the right. This panel shows the average RMSE of extended forecast as a function of forecast time. So the extended forecast with bias corrected forecast model with dense neural networks or LSTM produced much better accuracy compared with the case with polynomial fitting or linear regression. So, so far we explored the bias correction using neural networks with the analysis time series as a training data. But that approach has one limitation when observation and analysis time interval is much larger than the time interval of numerical integration of forecast model, DT. And this is actually the case in reality. For example, the most operational weather radar provides a forecast every 5 minutes. So delta T is 5 minutes. This is very frequent, but still larger than the numerical integration time steps, which is usually a few seconds. So in those cases, a bias correction term, estimated term, may not simply correspond to the missing term in original equation. So there are two ways of applying the bias correction to the forecast model, but in both ways there is an limitation. First way is the direct addition. So we can directly add the bias correction term to the forecast every delta T. But this causes well, jumps in forecast time series every delta T. And another method is linear approximation. So we can approximate the bias correction term in the original forecast equations by the estimated bias correction term divided by delta T. So this is popular approach, but this may cause a large error when model state rapidly evolves during delta T. In other words, this may cause a large error when the system is strongly nonlinear. So, our suggestion is what if we can directly model the tendency term, this term, by neural ODEs. So this is the last slide. So we have considered the model bias correction with data simulation using the analysis and the forecast with the time interval delta T. So if we use linear regression or neural networks to estimate the correction term, that correction term is, well, the difference between the forecast and, well, analysis and every delta T. But if we use neural ODE for this purpose, neural ODE estimates the right-hand side of the forecast, the dynamics, the basic function. So when combined with the known imperfect model equation, we can estimate the unknown missing term directly. So this is basically our suggestion, and we are going to implement and test this idea in the near future. And I would like any suggestion or concerns about this idea. So this is the end of my talk. Thank you very much.
Thank you very much. So, are there any comments or suggestions, questions?
I may have one question.
Yes.
So you plan to learn a correction of the bias to the model. using a neural ODE operator, due to the fact that in the context of data assimilations, the observation is often partial. Is it something challenging, and is it more? Will it be more easier to work on low-dimensional representation of the dynamics, maybe using an operator such as a generative model to go to the space of you consider, or directly on the high-dimensional space?
Yes, that is an important point. Well, yes. Yes, I think we have to find a way to find this function in a low dimensional space if we implement it to the weather forecasting model, for example. So if the original model equation has a high degree of freedom, even if this equation is high dimensional, it would be difficult to directly estimate this in high dimensional space. So we have to implement some dimensionality reduction. Yes, that may be the challenging point.
And my second question is, you made a mention of neural CDE. Do you have some example of geophysical process that cannot be stated as Bayesian, because it could be relevant in this context?
Sorry, could you say it again?
You made a mention about another neural ODE version, which was neural CDE in previous slide.
Yes. This one?
Yes. Do you have an example of data assimilation context where the process is non-Bayesian, and because it could be relevant in that context?
Well, no, actually, we have not considered the sufficiently how to apply the idea of neural CDE in data assimilation context. Maybe it's better to model in this way, but that this point has not been considered sufficiently. This is a future work. Sorry.
Okay, thank you very much.
Okay, thank you. And are there any other questions?
I have maybe one question, but first of all, I would like to thank you, Arata, for your nice explanation and state of the art of this field. It was very interesting, and yes, something that is not very clear for me. Can you come back to your experiment, and especially the step 2 in your algorithm?
Yes.
Yes, I'm not. I'm trying to understand if you apply your bias correction to all the members. I mean, is it the same bias correction for all the members, or is it a different one for all the members?
Do you mean the ensemble members in RIKEN?
Yes. So here in your
yes.
red box, so I think it's applied to the mean, right?
Yes, that's right. Yes. So we apply the bias correction for the mean state, ensemble mean of the forecast, and ensemble perturbations remains unchanged.
Okay. And is there a way to apply this correction for each member and to have a different correction for each member? in that case, I mean, in that case, you could also increase PF. You see and it's a kind of inflation of your covariance, but an inflation with a physical meaning, not ad hoc inflation. So I think there are a lot of possibilities, and it can be very interesting to apply a different bias for each member.
Yes, that sounds very nice idea. Yes, that's so. So it's not an easy question which way is better, but yes, that makes a difference if the time evolution has a strong nonlinearity, and yeah, this may affect. This may work as a one kind of
Inflation.
Yes, inflation.
Yeah, but I think it will be intelligent inflation compared to classic multiplicative or additive inflation.
Yes.
So I think you are on a good way. Thank you very much for your presentation.
Thank you very much.
Yeah. Are there any other questions or comments? Yeah, to follow up Pierre's comment about applying the bias correction to each ensemble member, in principle, I think if we have XF, then we can estimate the bias based on the XF. Not just the XF, I think the time series, I think. And then we could apply different bias correction to each ensemble member. That may complicate the situation for the LETKF because we have the covariance coming from the bias correction. And if the bias correction, so if we have a dynamical system, including the bias correction as the dynamical system, then, so we consider this term G as part of M, then it makes sense. But I'm curious if that is possible. But it's an open question, and I don't know what happens to the LETK.
Okay.
Yeah.
Any other questions, comments? Okay, if not, we move on to the discussion part.